Okay, so we now start the second section of the first chapter of topics in algebra, which involves mappings. Now we already know what mappings or functions are, but here the author has taken the view that mappings are defined by their graphs. So accordingly, here is the definition. Let S and T be two non-empty sets. A mapping from S to T is a subset M of this Cartesian product S cross T such that for every element in the first set there exists a unique element T in the second set such that the pair S comma T belongs to M. So according to this definition, there are two sets S and T and both are non-empty, and we say that a subset of this Cartesian product S cross T is said to be a mapping from S to T if for every element in the first set there exists a unique element in the second set such that this ordered pair is in M. Note that this makes sense because S cross T has such ordered pairs. Now M will contain in particular those ordered pairs that satisfy this condition. Okay. Now it looks somewhat strange that we are saying that a subset of S cross T is a mapping from S to T, but it's basically the same thing. What we already know as mappings is we have just said the same thing here in a different manner. So that's why there is a remark. Although we define a mapping as a subset of S cross T we should think of it as a device or mechanism that transports us from S to T, and this is how we generally think of mappings, right? Because we think of mappings like devices in which if we put some element of S as an input, then we get an element of T as an output, or we sometimes also think of a mapping from S to T as a device that physically transports us from S to T. We sit at one element of this set S and we end up at some other element, at some element of the second set T. So that's how we think of mappings, and that's how we should think of mappings. This definition serves to make the idea more formal and rigorous, but we should think of mappings in the way we always do. Okay, now we develop some notations for these things. Most of us already know about these things, but since someone has requested a video on this section, so you treat it like we are again going through the things for once. Okay, so most of what we are discussing here is already known to you in one form or another. So we develop some notations, this also you know. A mapping, okay, let me write it like this: if sigma is a mapping of S to T, we express this by writing like this, or sometimes also like this, where the name of the mapping appears above this arrow. That's how also we sometimes denote the fact that sigma is a mapping from S to T. If T belonging to T is associated with S in S by sigma, we say that T is the image of S under sigma, and we write this, or T equal to S sigma to denote this fact. So we are saying that a mapping associates with every element in the first set a unique element in the second set. That unique element T is said to be the image of that first element S under the mapping sigma, and we denote this fact by either writing like this or like this. Now here this may be somewhat unfamiliar to you. T equal to S sigma, you are more accustomed to seeing like this. T is equal to sigma of S. So there is a different type of notation that the author uses here, where he writes the mapping on the right side of the argument or the input. Note that we write the mapping sigma on the right. There is no overall consistency in this usage. Unfortunately, both the types of notations are in use. Algebraists, people who deal with algebra, who study algebra, often write mappings on the right, like what we have done here. Other mathematicians write them on the left. But the question is, why should we adopt two different types of notations where clearly one suffices? The answer will be, you will realize why this is done when we introduce composition of mappings, which will come at one part here in this series of videos itself. In fact, we ourselves would not be absolutely consistent in this. That means sometimes we will use, sometimes we will write the mappings on the right, sometimes we will write them on the left. If we want to emphasize the functional nature of sigma, we may very well write T is equal to sigma of S. Functional nature means here we are viewing sigma as a device that gives us an output when an input is given. That's what we mean by the functional nature of sigma. Sometimes we will to emphasize that sigma is a function which gives us something when we feed something into it. to emphasize that fact, sometimes we will write like this instead of like this, but this is also, in fact, this is how we will write mappings most of the times in this book, and the reasons will become clear. Okay, let me put some ink first. Now, since this issue has come up, let me also tell you that there are other ways of writing the same thing. Some people also write, instead of writing like this or this, some people write t equal to s to the power sigma, but I don't know why people write like that, but I have seen it in some book where the mapping appears as an exponent. We will not use that here. Okay, now next we explore some examples of mappings. Examples of mappings. Note one thing, that those of you who have already seen the section on functions in Tau's analysis in my videos, you can see that in our definition of a mapping, we have taken both S and T to be non-empty. That means we are not going to consider that particular things known as empty functions or empty mappings. We have no need for those things. So that's why in this book the author does not bother to deal with empty mappings. For us, these sets that appear in a mapping, he also does not say that this is domain or this is range. He just simply mentions them as sets. So for us, these sets are always non-empty. So before we begin the examples, we mention that. In all our examples, the sets involved are non-empty. Okay, so this is the first example. Let S be any set. Any set means any non-empty set, because we have agreed to only consider non-empty sets. Define a mapping from S to itself by for every S in S. So this symbol is known as the Greek letter iota. I should have written like this. So iota is a mapping from S into itself, where it maps every element of S to itself. That means it does not change the input. Whatever the input is, the output is also the same thing. So note that according to this definition, every element of S is being mapped onto a unique element of S. So that condition must always be verified whenever a mapping is given to us. Otherwise, it's not well defined, or in other words, it's not even a mapping. So this is a mapping and it has a name. This mapping is called the identity mapping on the set S. Okay, so this is a mapping. Then the next exercise, example. Okay, so for the next example, that is the constant one. Okay, let S and T be any sets and let T not belonging to T be any element. Okay, so we now have any two sets S and T, and we have arbitrarily chosen any element T naught in the second set T. Define a mapping tau from S to T by S tau equal to T naught. For every S belonging to S. So here what we are doing, we are mapping every element of S onto the same fixed element T naught in capital T. So here also note that every element in S has a unique image. So this is a mapping. In fact, one can call it a constant mapping, where the mapping has the constant value T naught. Sometimes the mapping, instead of calling it tau, we call it T naught itself by abuse of notation. Although T naught is an element in T, but sometimes we call the mapping itself as T naught. For example, if there is a mapping on the set of real number that maps every element, every real number onto say the number 1, then we will sometimes call the mapping itself 1. You will see this in some places. Okay, the constant mapping 1, we say like that. So in that sense, this can be called the constant mapping T naught. Although we cannot use D because there may be many different such mappings depending on what S and T are. Okay, so now next, the third example. Let S be the set of positive rational numbers and let T be J cross J, where you already know what J is. J is the set of integers. Okay. Now given S belonging to S, there exists, okay, so what does it mean when we say that S belongs to S? It means that small s is a positive rational number. So by the definition of a rational number, small s can be written as a ratio of two integers, and we can choose those two integers to be positive. So there exists positive integers m and n that are relatively prime. And S is equal to m divided by n. Okay, so not only do there exist positive integers for which this ratio becomes S, but we can in particular choose those integers in such a manner that they become relatively prime. So let us just see a small example of this to better understand what we are saying here. Suppose in place of S we have the rational number 0.5. It's a positive rational number. So we can write this number as 1 by 2, 2 by 4, minus 3 by minus 6, 3 by 6, etc. So there are many ways of representing the same rational number S as a ratio of two integers. But among them, this of course we will not consider, because here the numerator and denominator are negative integers. So we first of all we want positive integers, and then we want them to be relatively prime. There should not be any factor common to them other than 1. Okay, any positive factor. You see that 2 and 4 are not relatively prime, both are divisible by 2. Here both are divisible by 6. So once we find such a thing, I mean, we of course, okay, one question may arise: if a rational number is given to me, is it guaranteed that I will always find a pair of positive integers for which the ratio is the rational number and they are relatively prime? And the answer is yes. How? Because you see, if they are not relatively prime, then you cancel out the common factors. Ultimately you will end up with relatively prime positive integers. Or if you want to transform a ratio like this into a ratio like this at once, what you do is that you divide both the numerator and denominator by their greatest common divisor. That will turn the ratio into 1, where the numerator and denominator don't have any common factor other than 1. Okay. So having understood this much, now we are going to use this to define a function from S to T. Now define tau from S to T by defining the image of S to be equal to the ordered pair m comma n. Okay. Now note that although we have said all these things and we have defined the function like this, we have to make sure that whatever we have done is well defined, because you see, I have a positive integer. I have been able to write it as a ratio of two positive, I have a positive rational number. I have been able to write it as a ratio of two positive integers which are relatively prime. Now, is it not possible that I may have two other positive integers whose ratio is also equal to s, and these two are also relatively prime? If so, then in one hand this will be equal to m1 comma n1. On the other hand, this will also be equal to m2 comma n2. So the fact that each element of the first set has a unique image under the function will be violated if these two things are not identical. So we have to make sure that that is the case. In other words, we have to verify that the function we have defined is well defined, and that's what we are going to do now. Okay, I leave the issue of availability of m and n for a given s to you. That is, if we are given a positive rational number s, then there exist positive integers that are relatively prime such that their ratio is s. Okay, you convince here. I have already said how to do that. Divide them by GCD. You put it into words. Okay, now here we are going to deal with the existence is there. Now here we are going to deal with the uniqueness. Let s belong to s, and let m1 n1 m2 n2 be positive integers such that m1 and n1 are relatively prime. Recall that this is the notation for the greatest common divisor of m1 and n1. This is one condition. m2 and n2 are also relatively prime, and s is equal to m1 by n1, and which is also equal to m2 by n2. Okay, then m1 n2 is equal to m2 n1. Cross multiplying, we get this from this equation. This implies, since these are all positive integers, we get the fact that m1 divides m2 n1. Because m2 n1 is an integer multiple of m1, n2 is an integer, so that's why. Now, since m1 and n1 are relatively prime, from a property of divisibility of integers, then m1 has to divide m2, because it cannot divide n1, or there is no common factor. We must have m1 divides m2. In a similar manner, we also, you can see that m2 also divides m1 n2, and since m2 and n2 are relatively prime, m2 has to divide m1. since M1 and M2 are positive, we thus have M1 is equal to M2. This is the only case in which each one can divide the other. Thus, from M1, M2 equal to M2, N1. If you cancel out M1 and M2 from both sides, we get N1 is equal to N2. Hence, M1 by N1 tau, which is equal to M1 comma N1. Now this is equal to M2 comma N2, and that is equal to M2 by N2 tau. This proves that the mapping we have defined is well defined. Sometimes showing that a mapping is well defined will be so easy that you can almost see that it's true. You don't have to do anything, like in the case of the previous two examples, but sometimes you may need to